started, and then I'll hand over to Xiangyu. So the topic we are going to share about today is experiment. So basically, agentic AI for experiment control, and also data analysis. And I'll talk about basically the experiment control part. So our initial motivation of developing agentic AI for some background. So I work at the advanced photon source of the Argonne National Lab. So APS is basically so-called a synchrotron light source. This is basically a huge X-ray light source that generate high brightness and high coherent X-rays. And around this light source, there are lots of experiment end stations, which are called beamlines. Each beamline basically uses the X-ray to do their own measurement, and like you have different lots of different types of material characterization techniques, which including microscopy and fluorescence microscopy kind of experiment, where some beamline also do tomography and also spectroscopy experiment. So in their measurement, we often encounter the problem of, say, searching for a small feature in a large sample, which is a very common scenarios for the microscopy folks. So let's say imagine that you have this whole mouse brain, which can, for the size can be around the scale of centimeters, and you are looking for some stained cells like this, and the cell size is probably just on the order of 1 micron. So oftentimes you'll encounter this kind of like searching for a needle in a haystack kind of problem. And because you need to have very fine scan or fine resolution to be able to see the cells, that means your field of view is interested because your detector only have a fixed number of pixels in size. So if your pixel size is very small, in order to resolve this kind of a small features, that means the area that you can scan in one image is also going to be very limited. It might be just a small fraction of the whole size of the sample, and sometimes you probably don't really have a good idea of where exactly your sample is located. So that just pretty much leaves you the only option being searching, like doing a series of small and fine resolution scans across the sample, and for each one manually check the image and see if the feature you are looking for is inside, and then move it to the next location. But now with Vision LLMs, we can do this automatically by simply building an agentic loop and tell the LLM that I'm looking for cells that looks like this sort of small gray dots. So if you see this kind of things, let me know. Otherwise, call the tool and scan the next location. So this can very dramatically reduce the human involvement and the labor intensiveness in the experiment. And another thing is, so far we are just talking about one particular type of sample, but in a beamline, we are user facilities, so we have users coming from all different institutions, all different backgrounds, and they send us different samples. It's not just about biological samples, but there are also things like microelectronics or material science samples such as battery materials. So with traditional method, when you like do this kind of a feature search or pattern recognition, you can probably train a model or design a computer vision method to match the features, but you can't do this easily for every different types of sample. You always either have to redesign or retrain your model to make this kind of feature recognition or pattern recognition work for different types of samples. But with the foundational Vision LLM, we can pretty much just change our prompt every time to make it work for lots of different type of samples. So the agentic workflow that I was talking about is essentially abstracted in this kind of flow chart. So basically, the user first says, "I want to look for this feature," and the LM has essentially the tool. It has two tools. Sometimes it can be combined into one. So it has a tool to acquire an image of the sample at a given location. So in this case, the LM can call the tool as to acquire at a certain X or Y, and it gets this image. And then the LM sees whether if there are cells or any feature that matches the user's description in this image. If there isn't any images, then we call the tool again and move them to the next location. If the images are there, then we are done. Right. So the main advantage is that we don't have any code. We don't need any redesign for different types of samples. So after verifying that this works, we then move to think that about why don't we build a more generic kind of a framework that can use that uses an agent to control the beamline and talk with the humans through a natural language interface. So conceptually, this is actually very simple. We just scale up our framework by adding more tools to the agent. So now, in addition to just simply acquiring images, we can also expose tools to move certain motors. It can be the motor that controls the focusing device, or it can also be some setter interfaces to set, for example, the shutters, the detector, and also some motor positions in the beamline. So with this, we can realize the control for lots of different instruments for many different kinds of applications. So overall, the framework that we have built is called Experiment Automation Agents, or EAA. The architecture looks like this. So what's central in this whole architecture is what we call a task manager. So for a typical generic LM agent chat loop kind of application, we just have a pretty generic chat loop here, and also the task manager manages the LM client, it manages the contacts, and also maintain the registry of tools and also skills. And also because our application involves images, we need to give user a way to visualize the conversations and the processes. So we also have a web UI, and the task manager hosts a runtime controller that talks to the web UI. And meanwhile, we also have other components that you can probably commonly see in lots of agentic frameworks such as RAG, skill library, and also for tools, we have both built-in tools that allows the LM to access the file system and do coding and also render images. This image rendering tool is useful because in many scenarios, the scientific images are floating point and they might have very abnormal dynamic ranges. And the image viewing tool allows the LM to, for example, set the dynamic range to a certain percentile of the image to exclude the effect of those outliers. And for instrument control tools, we package them into MCP servers so that the LM can talk to the MCP servers to move some certain motors or control the instrument devices. So at this point, so everything is actually pretty generic. Like everything, I would say most of the things are what you can find in a very typical or generic agentic workflow. So what's special, or let's rather say what's the main challenges in building an agentic framework for instrument control. From the engineering point of view, there are two main challenges. The first is that the tools can probably yield images. So, for example, if you have a tool that allows the LM to acquire an image at a certain XY location, you probably want the LM to see the image using its vision capability. But that means we need the tool to somehow return the image, but this is not always supported by all the APIs. So here, one of our constraint here is we use Argonne's service called Argo, which is a LM relay platform. At the early days, only OpenAI's completions API interface was supported, and that interface doesn't allow your tool responses to contain images. So that's one challenge. The second challenge is for instrument control. Um, so if we wrap the tools as MCP servers, these MCP servers have their own async event loop in the gateway. But in the meantime, some of the instrument control libraries also have their own async event loops. So for example, we are using so very commonly people at the APS are using a framework called Blue Sky to control their instruments. And Blue Sky does have its own event loop, and we have this kind of experience that if you if you directly call blue sky functions in a async function, it's gonna crash because of this async event loop unsafety. So for the implementation of the tools, we are taking this kind of scheme to ensure that first we can return the images generated by the tools properly to the agent, and also second, we can make sure that all of our tools can run normally without any threat and safety or async event loop crash. So basically, the idea is that for the tools, we want to separate them into a front end process, or sometimes I would rather say a gateway process that serves all these asynchronous functions that's directly called in the MCP client on the agent side. So here we only so here we don't directly call the functions that runs the instruments, but rather we put all the calls to the instrument control library in a different process, which we'll call instrument worker process. And inside of this process, everything is synchronous and blocking. So we don't have any higher level or upper layer async here, so that nothing crashes with the intrinsic async loop in the worker processes or the instrument control libraries. And the MCP gateway and the worker process talk through ZMQ, and the ZMQ call is also blocking. It's essentially made blocking so that we don't introduce any unwanted async. So again, the key idea is to make sure that the instrument control functions are all called in a synchronous loop. In some cases, the beamlines are using this feature called a Blue Sky Q server. So Blue Sky, we just mentioned, is a library for instrument control. And the Q server is a feature of Blue Sky that creates a different server that listen to requests to move some certain instruments and perform certain instrumental tasks. And this server runs on its own process. So in that case, our MCP only need to implement a front end or a gateway that makes calls to this Blue Sky Q server. So the philosophy of these two different cases are actually very similar. They are both to separate the instrument worker processes and the MCP gateway processes into two different processes. And for passing images, our current solution is to basically return. So we either save the image to a PNG file on the hard drive on the tool site, and then return the path to the image file. And on the agent side, we capture this payload and load the image, and then basically encode the image and send it to the LM in a follow-up system message or user message. Alternatively, we can also encode the image data into base64 and directly make the tool send the encoded data back to the agent harness. And we have some contract between the agent harness and the tool so that we can intercept this kind of payload. We get the encoded data, and then again we send the encoded image in a follow-up system message or user message so that the agent can see the images. So here we have a video that shows one example of how we use this agentic framework to look for a feature in a large sample. So here we have a test sample that contains a so-called Siemens star. So Siemens star is a common testing pattern that is basically a disc-shaped object with lots of radiating spokes. So we are asking the agent to look for this kind of feature in the sample. And we tell the agent the search range. It has to be within this range, and it should use a field of view size of 300 by 300. The unit, I believe, is in micron. So as you can see, initially the agent make a tool call to scan at this location, like the starting point of the search grid. And when it calls this tool, it triggers the backend acquisition process. So the instrument is activated to collect the images. And once the image is collected, it will be sent back to the agent. And then, as I said, it will be send to the LM in a follow-up user message so that the LM can see the image that it just collected. So the LM said, okay, the star center is not visible in this image, so I'm gonna move to the next location. So it just calls further tools, makes further tool calls, and this plot that we are showing here visualizes the position of the scan in the sample. So you can see it moves constantly and approaches the sample. So for the sake of time, I'll just fast forward this. But eventually, you can see. So this I hope this shows the idea. So there's another example which I'll also probably just fast forward. So this is a different application of like telling the LM to find the optimal focus of a microscope by moving the position of a kind of focusing device called a zone plate. So zone plate is essentially equivalent to the objective lens in X-ray microscopy. So just understand that as the objective lens. So we want to move the position of the lens to find the best focus, which gives us the sharpest image. So basically, the procedure is like we first do a 2D scan at a given location, then run a line scan across a designated feature, and then our tool will perform a Gaussian fitting, and then the full width at half maximum will be returned to the LM so that it can see basically the width of the current feature. So the sharper the feature is, the smaller the full half maximum will be. So after that, the LM should adjust the optics parameters, which is the position of the lens, and then do a 2D scan again. So we have to do 2D scan again because every time we change the zone plate parameter, the image is going to drift. So after that, our harness will run an image registration step to basically calculate a correction to fix this drift so that when we do this 1D line scan, we're always scanning the same feature. Right. So basically the LM just follows this procedure and it makes pull calls alternatively between like doing 1D scan, 2D scan, and setting the zone plate Z positions. Right. So this is at the very beginning. At the very beginning, everything is extremely blurry, so we don't have a very good fit. But after the LM changes the zone plate Z position, we are gonna have a better focus. Okay, which should show up here. Okay, so then the LM just keeps adjusting the Z position of the zone plate until it sees the sharpest image, and also from the images you can see that is the sharpness gets better and better. Okay. Uh, right. So another thing that I wanted to mention is that our current vision is that so this kind of system can be used not only for LM driven processes, but it can also be used for processes that are more suitable to be driven by logic or by mathematical algorithms. Because there are certain processes such as Bayesian optimization or rule-based workflows that are better to be driven by logic instead of driven by an LM because it doesn't really give you any additional benefit if you already have a very well-defined rule-based workflow or mathematically defined workflow that's shown to work very well. So in that case, we want to make our framework to support not only LM-driven processes, but also this kind of processes that where the logic-driven components are taking a larger fraction. And also the benefit of like squeezing all these different types of workflows into the same framework is that we can first make them reuse the same web UI, which can be very handy for the scientists to visualize the result of a certain process. And also we can use the agent loop as the universal entry point to all these logic-driven algorithms. So this is the picture that we are currently thinking. The most important thing is the sub agent tool. So basically this generic task manager runs a chat loop. So this is basically our entry point, which is also a chatbot. So the user can talk to the agent in this chat loop and say, I want to do a Bayesian optimization based focusing process. Then this agent will use the sub agent tool to launch this process. Yeah, so despite that, like this process is totally Bayesian optimization, there's no LM involved inside. It can still be triggered and be launched from the agent-driven process through more like a natural language interface. So here is one example that shows what I was talking about. So here from the main chat agent, we say we want to basically start a focusing process driven by Bayesian optimization, and here are all the parameters. So after sending this, the agent is going to call the sub agent tool, which launches this particular sub task manager that runs the Bayesian optimization. Then it's going to open a new tab here. So as you can see, so in this new tab, we are showing the process of the kind of analytical Bayesian optimization focusing process. And also we have this visualization tab, which shows the update of the process in real time. So here we are doing a Bayesian optimization. So the user will be more interested in the current parameter, the search history, and also what's the posterior predictions from the Gaussian process, which includes both the estimated values of the focus and also the uncertainty. So in this plot, we are gonna dynamically show everything. And after this process finishes, the conclusion, which is basically a summary of the search history, will be returned to the main agent. So that's why you're seeing this here. And so the main agent also has access to what happened in this task manager, and it will give you further analysis if you ask it for anything. Okay. Right. So this is my last slide, and I want to thank my collaborators. So without further ado, I'm gonna hand over to Xiangyu, who's gonna talk about more on the data analysis side.
Okay. So Ming talked about how to use those foundation models and building agentic workflows to automate experiment control, and I will talk about how we can use them to do data analysis, which is another very important aspect of X-ray science. So many of the agentic workflows I'm building are for this computational imaging technique called ptychography. So essentially, we collect a series of raw diffraction patterns, and we're trying to reconstruct the images of the object using some iterative optimization solvers. So here you can see some example reconstructed images, and this might be a little bit subtle, but if you look closely, there are some artifacts on those images, and this is a very typical for typography because this is a pretty challenging inverse problem. So traditionally, how beamline scientists handle those artifacts is that they look at those images first, and then they give their diagnosis, and then they will take some actions based on their past experiences working with this type of samples or this type of images. Um, so essentially, we are trying to automate those two decision-making steps in this type of typography data analysis. The task one, essentially, we are trying to use vision language model to look at the images and tell us what type of artifacts are there. And task two is essentially we want the large language models to be able to look at the diagnosis and also meta information about the experiments and data set and tell us what kind of actions we need to take to eliminate those artifacts. So the first step we did is actually benchmarking, and because there are many different ways to use those models, and I think the details of these slides doesn't matter for this talk, but the takeaway is that we do find for different tasks there are different best recipes. For example, for this vision task, you do have to do some fine tuning, but for this large language model recommendation task, sometimes you use a larger model and you do not really need to do a fine tuning, and that's fine. So with those best recipes we obtain from those benchmarking, we can build this type of agentic workflow that help us fine-tune the parameters of this typography reconstruction automatically. So essentially, the user will interact with this tycho agent, and the tycho agent will collect all the metadata and based on its large language model capability and suggest some parameters. the coding agent will codify those into a runnable script. We run the script and do the reconstruction, which can be like hours, and then it will generate an image. And the vision language model will look at the image and tell, basically give us some recommendations in terms of what kind of artifacts are there or what's the quality of the reconstructed images. And the tackle agent will look at those diagnoses and use the large language model again. So now we have a closed loop. So we build this workflow for X-ray tachography, but this can also be applied to electron tachography. So this is from our collaborator at Rice University. So essentially, traditionally, to handle this type of data, you may need to run Bayesian optimization for hundreds of iterations. But with large language model, because it has the unstructured knowledges like coded in the markdown files or past papers, it can very efficiently iterate the process and get a pretty good, like improve the quality of the reconstruct images in like 2 or 3 iterations. So recently, we've been trying to see how far we can go with this agentic workflow because tuning the parameters can only get us so far, and the more fundamental way of improving our data reconstruction quality is to improve our algorithm. So essentially, you can see that many of the components are actually the same. For example, the coding agents, the analysis agent is still using the vision language model. But essentially, we ask the coding agent to generate some regularization function. So we have a code generation a loop type of agentic workflow. And in terms of this type of simple algorithm workflow can already help us. For example, this is an integrated circuit data set. You can see that this is a baseline. You can see that we have to do like 10,000 iterations to get a image without the grid artifacts. But with this type of agentic workflow, we discover a regularization function that help us reduce the time that we can get to this similar quality. For example, you can see that at around 4,000 iterations, we can already have an image that doesn't have this kind of grid artifacts. And also because it's large language model, we can also do some in-depth analysis by looking at these reasoning traces and actually plotting how the different techniques evolve during this discovery process. So we are not only getting a better regularization function, we are also learning something about the whole process. And this is the recent work collaborating with Ming. So essentially, this previous agentic workflow is tailored for tychography, but we want to make it more general because many of the data analysis we encounter every day is actually unstructured because it doesn't have a like really well-defined structure of the problem. What's the optimization problem? What's the loss? What kind of algorithm I should use? So essentially, we extended this idea and developed this new framework called CV-Evolve. So because of the time, I will not talk too much detail, but you can go to this is archive now. And we also open source the code. So essentially help us dealing with some unstructured data analysis problem where we do not really have a predefined structure where we know what kind of objective we are optimizing or what kind of algorithm we need to use. And I think at this time, like many people are already using coding agents like Cloud Code or Codex, and this is really changing the way we do data analysis because in the previous agentic workflows I introduced, we're basically defining how the agent should behave and how the information flow, the decision-making workflow should look like. But with coding agents and the models are becoming more and more intelligent, we found that maybe we do not really need to define so much of the structure of the problem. We can just provide some skills to the coding agents. And because the coding agent is very smart and also has access to the file system, we can essentially ask the coding agents to act as its own and make its own decisions. And because it's data analysis, not experiment control, we do not really, it's not like a high risk scenario. So we can just ask the agent to do the data analysis in a flexible way. And another thing I really like about the skill is that you can basically ask the agent to update the skill based on its past interaction with some data sets. So it's kind of like self-updating and self-evolving skills. And also, uh, so so this is demo. So because of the time, I will. So essentially, it's just a wrapper of the agent SDK. So essentially, it's running a headless cloud code underneath, and it essentially has the file system, the bash terminal, so that it basically it's like cloud code, but with the tycho skill, so that it can analyze the tychographic data sets. So also we have this data analysis portal for the beamline scientists, and we are also extending this type of agentic workflow for beyond tychography for some other type of data analysis like spectroscopy. So currently we're building this platform called Daughter XAS, which is an agentic workflow platform for X-ray absorption spectroscopy. So because of the time, I will not go into the details. So essentially, we found that agents and foundation models are really helpful, and it can help us automate the experiments and also help us automate our and accelerate our data analysis. Yeah.